Inside nearly every toilet tank is an automatic valve whose basic operating principle was invented over 2,000 years ago by Hero of Alexandria. Hero's version used a piece of cork floating on water to open and close a valve automatically. I rebuilt this ancient mechanism to understand how it works, and the results reveal an engineering lineage stretching back from ancient Alexandria to the modern bathroom. This simple machine helped make reliable plumbing possible, and reliable sanitation became one of the most important factors behind the enormous improvement in human health over the last 2 centuries. To understand how a floating piece of cork became one of the most common automatic controls in the world, we have to begin at the beginning, with the earliest machines that learned to use buoyancy. From the first time a caveman floated across a river on a log or inflated animal hide, people knew about the basic idea of buoyancy without ever understanding exactly how it worked. We have discussed the use of water as a source of power in previous videos, but in this one I want to tell you a different story about water. The story of how that little cork, resisting being pushed underwater or bouncing to the surface when released, turned into something that improved the world so much it is impossible to calculate. The first devices to use water, not as a source of power, but for other properties such as measurability, were known as clepsydra water clocks, and they came from ancient Egypt. These were simple clay jars with a small hole in the bottom. A certain amount of water would be poured into the jar, and time was measured in how long it took for that water to run dry. Not having a standard hole size was a challenge to uniform timekeeping, as was the fact that this was really not a clock at all, but more like a water version of a sundial. If your jar went dry and you didn't fill it up, you lost track of the time. These were normally used to keep time through the night until the sundial would work again. They were also known as night clocks for this reason. A certain Hellenistic engineer by the name of Ctesibius of Alexandria lived in that technically advanced city and was, along with the much later Hero of Alexandria, part of the reason behind many of the clever mechanisms we associate with that location. Now, Ctesibius did two things to improve the water clock. He linked 3 jars together at different heights. The first jar poured into the second jar from a hole or tube here near the bottom. The user needed to glance in every so often, check the level, and top up the water, but critically, they didn't need to carefully measure it. If we look at the second jar, we will see that it had 2 holes, one at the bottom that flowed to vessel number 3, and an overflow hole at the top like an old sinker bathtub would have. This kept the water level in jar number 2 at a constant height, and therefore kept a constant rate of flow into the third and final vessel. This third vessel is where we see the float first used in a machine. As the water level rose in the jar, it lifted a drum-shaped cork float. In an early version of the clock, there were some gears and possibly pulleys attached, but later versions refined this system a bit more in the following way. The upward rising motion of the float raised a pointer that would then point to the correct time on a carefully marked cylinder placed offset of the last jar. These clocks were the first where a physical pointer or a hand of some sort pointed to the time. We still call the pointers on a clock the hands of the clock. There are quite a few other intriguing things about the Ctesibius water clock, but what I wish you to observe is how the rising motion of that float was harnessed. We have a combination of water, a drain, and a float with something attached to it that allows a way to time an action into a machine with very little effort. No one really understood the deeper principles behind what was happening here until Archimedes came about 30 years later and established the mathematical basis for displacement, buoyancy, floating equilibrium, and vessel stability. Vitruvius described many variations of water clocks and hydraulics in his 10 books on architecture, which preserved many centuries of Greek and Roman hydraulic machinery, but the floats pretty much did the same thing as always, rising and falling when the water level did. The first machines we know of that did something different with floats were those made by Hero of Alexandria. Living in the same town as Ctesibius, but some 200 years later, Hero of Alexandria needs no introduction, and is well known for his early steam engines, air-powered devices, and clever temple machinery used to trick worshippers into thinking their offerings were having a physical effect. Someday, we may have to do a deep dive into Hero because many of his devices are far more sophisticated than people realize. But hidden among all those dramatic steam turbines and temple effects is a much simpler contraption that I think may be ultimately one of the most important devices in this entire story. Let me introduce you to Hero's self-filling goblet, a drinking cup that refilled itself whenever someone drank from it, most likely in a temple or party trick context. The original explanation in my translation of Hero is honestly difficult to follow, but the underlying principles become clear once I started tracing out the water's path. In summary, this is what's going on. Vessel AB acts as a hidden reservoir, much like the upper vessel in the old Ctesibius water clocks. Pipe CD feeds a lower trough concealed beneath the goblet, while the goblet itself is connected to that trough through another tube. The important thing here is that the goblet and trough share the same water level through the principle of communicating vessels. Lower the level in one, and the other level falls with it. Inside this tank, Hero placed a cork float connected to a lever and valve arrangement. When the goblet is full, the water level in the tank is also high, and the cork is strongly lifted upward by buoyancy. In this position, due to buoyancy, the cork forces the valve shut. But the moment someone drinks from the cup, the level in both the goblet and the tank begins to fall together. As the tank level falls, eventually the float drops far enough down that the valve opens and the water from the reservoir at the back begins flowing into the tank and the goblet. Then, as the level in the tank rises, the cork does as well, rising upwards and shutting the flow back off. This lead weight that Hero added to the opposite side of this lever attached to the cork is especially interesting because it reveals he understood something about the system you would probably only discover from trial and error building one. Without some sort of counterbalance, the cork might jam itself too firmly against the valve opening or fail to move reliably at the correct moment. The weighted side of the lever allows the threshold for action to be tuned very delicately. By the medieval period, the float had moved from the world of clocks and temple novelties and entered the practical realm of urban water storage. Medieval cities increasingly depended upon cisterns, rooftop reservoirs, and controlled water storage systems because reliable flowing water simply did not exist in most towns. In fortified castles and monasteries, these systems became especially important because an overflowing or contaminated cistern during a siege would be catastrophic from the disease. The engineering literature from the late medieval world increasingly shows concern not merely with storing water, but with how to regulate it and maintain stable levels inside tanks and reservoirs. The Islamic world became one of the greatest centers for hydraulic experimentation, preserving and dramatically extending many Greek and Alexandrian mechanical traditions. Engineers such as the Banda Musa brothers and later Al-Jazari built elaborate fountain regulators, self-adjusting basins, hand-washing automata, and water clocks that relied heavily on float regulation. In many of these machines, the float had evolved beyond simply rising and falling with the water level to actively controlling valves, switching water paths, and starting timed motion sequences. By the Renaissance, the float mechanism had become deeply embedded in European hydraulic engineering. Engineering notebooks from that time show increasing obsession with pumps, cisterns, canals, fountains, and self-regulating water systems. One of the more interesting drawings by Takola shows this large tube with a float in it. There are details missing from the drawing, but here is what I think is going on. This is a cistern that collects rainwater, and as the level rises, so does the float on the chain. Near the end of its limits, the float pulls open a door at the bottom, and the entire saved-up column of water floods out at once. We don't know what application Takola was thinking of, but maybe it would automatically flush a water or sewage system periodically. At any rate, it would keep the cistern from getting so much water in it that it would overflow. Takola's cistern float is doing something similar to the Hero of Alexandria's water goblet, but instead of controlling the water input, it controls when all that saved up water is released. Renaissance engineers inherited the ancient Greek and Islamic hydraulic traditions and combined them with the rapidly growing urban infrastructure needs of Europe. Cities required fountains that would not overflow, reservoirs that maintained stable levels, and water systems capable of operating continuously without constant supervision. This is the period where we see float-regulated valves appearing more recognizably in forms used later in cisterns and tanks. Ramelli's book in particular show how Renaissance engineers thought increasingly in terms of systems regulating themselves through balance, pressure, and controlled flow. By this point, the float had entirely ceased to be a curiosity and had become a part of practical hydraulic engineering. The Industrial Revolution moved the humble float into machines that were far more dangerous and important: steam boilers. Steam boilers required the careful regulation of water levels because allowing the water to fall too low could destroy the boiler or cause catastrophic explosions. Engineers therefore began using float-regulated feeding systems and automatic level controls to maintain safe operating conditions. Now the principle of buoyancy was no longer simply filling goblets or controlling fountains. Instead, it protected factories, locomotives, and steamships from disaster. As modern cities expanded during the 18th and 19th century, the problem of water regulation was enormous. Urban reservoirs, elevated water towers, cisterns, and municipal plumbing systems all required automatic shutoff mechanisms capable of maintaining stable water levels without overflowing. This is where the modern float valve finally emerges into view. This mechanism consisted of a hollow floating ball attached to a lever operating a valve. This became standardized in the late 18th and 19th centuries. Mexican scientist Jose Ramirez described a recognizable float valve system in 1790, and Edmund Cartwright later patented float valve systems in 1797. We have now reached the familiar mechanism shown at the beginning of the video, the automatic fill valve inside of a toilet tank. The same feedback principle first described in Hero's self-filling goblet now regulates the water level in modern toilets. If you remove the lid from the back of a toilet, at least one of a basic design, you are looking at the descendant in a line of engineering experimentation that stretched back through Renaissance workshops, medieval cisterns, Islamic hydraulic regulators, and all the way back to that floating cork in Alexandria. The exact materials have changed over time, of course. The cork float was later made out of wood, leather, rubber, and eventually plastic. The open tank became an enclosed cistern. Primitive lever arms became carefully tuned valves. But the underlying principle and mechanics barely changed at all. The water level falls, the float falls with it. The valve then opens, and fresh water enters the system. Then, as the water level rises again, the float rises too, until eventually the flow is shut back off automatically. The remarkable thing is not simply that this mechanism survived, but that it survived because it was almost perfect from the very beginning. It solves a genuine problem elegantly using almost no energy at all. The float does not need gears, springs, external power, or complicated controls. Gravity and buoyancy perform all the work automatically. The machine regulates itself simply because floating objects naturally rise and fall with changing water levels. Early toilet designs often wasted enormous amounts of water because the refill process was poorly controlled or entirely manual. Look at this toilet design from Elizabethan England. This toilet had a huge water tank at the back to flush the waste away. Yes, you could turn it on and off with this key, but it was not efficient at all. Every time you flushed, you would get a different amount of water. The float valve changed all that, allowing for a water tank that could refill itself automatically to exactly the correct level every single time without overflowing. It transformed the humble toilet from a luxury device into something practical enough for widespread urban use. And with the widespread use of sanitary devices like the flush toilet, the overall disease rates of the world began to fall. Like I said at the beginning, many factors have gone into the drop of diseases over the last 250 years, but the flush toilet was certainly one of them. The irony is that most people never notice this mechanism precisely because it works so well. It just sits there, hidden behind the tank wall of every toilet, a machine that stretches back 2,000 years of hydraulic experimentation. Hero of Alexandria's self-filling goblet never disappeared at all. It was sitting right behind you this whole time.